This is Perry Marshall. I'm here with Stuart Kauffman, and Stuart is with the Institute for Systems Biology, and for years he was with the Santa Fe Institute. And I met Stu because he had his 80th birthday party at the Santa Fe Institute called Stu Fest, and I managed to get myself invited to this thing. And we had some wonderful conversations, and I got to tell you, like, the crowd that Stu attracted, it was a great crowd, and I made very important connections. And there aren't very many crowds like this because it was a very interdisciplinary crowd. And I think there was like 40 science presentations in 2 days, and it was biologists and physicists and cosmologists and chemists, and it's like all and even people in the soft sciences. There were investors and entrepreneurs, or all these interesting people. And Stu is a pioneer in self-organization theory. Like, how does the world put itself together? And this is really a very different way of thinking about the world. And Stu has written a very interesting paper called "The World is Not a Theorem." And, well, it has very deep implications that we're going to get into it, but really, it pulls the rug out from under an entire philosophy of science that has dominated science probably for the last 200 years. So, like, this is not a trivial thing. And I know exactly what I'm talking about, and I know how audacious this is. And so just before we went live, Stu says, I don't think any journal is going to take this paper. Well, you might find one, but let's pick up right there. Stu, you're only pulling the rug out from under a century or two of bad assumptions. So, nobody's going to be bothered by that. So what's that like?
Well, hi, Perry. If what this is also with Andrea Roli. If we're right, we're pulling the assumptions out from Pythagoras, who said all is number. Then Newton constructs celestial mechanics, which is superb, and Einstein takes it to relativity, which is confirmed to 13 decimal places. Then it becomes quantum mechanics with Planck and Bohr and Heisenberg and Schrödinger, which is confirmed to 13 decimal places. This is the weirdest thing I've ever done in my life, and I've done some pretty weird things, including playing jazz drums at my Stu Fest, and I think I was not terrible. I think I achieved mediocre. People kept dancing. One background to this, Perry, is I published a book in 2000 called Investigations. I dimly realized that the universe, the Biosphere, the evolving Biosphere, was doing something that somehow wasn't computable. And that's a long time ago. It's now 26 years later. I understand more about it. It's very strange. I emphasize the word strange. So let me tell you what an affordance is. It was defined by Gibson. So he's a psychologist, and he knew what he was talking about. An affordance, an example of an affordance is a horizontal surface affords you a place to sit. So it is something that you can use to do something. Okay, so a stick affords you a way to hit your friend on the head. So an affordance is an X that can be used for Y. Now, in biological evolution, this is not just psychological affordances to do things as, say, human agents. All of evolution is about the coming into existence of new affordances, which are, for example, new physiological functions. I'll defend it in a minute, but let's get there. So your heart affords a means to pump blood to the rest of your body.
Yes.
Came into existence because they afforded that means. Or feathers on a bird afford a means to fly. They're flight feathers.
Or an iPhone affords a place for an app to be installed so Uber could exist.
Absolutely. They're all affordances. All of those are affordances. Affordances are opportunities.
Yes.
So hold on. Where I'm going to go is to talk about affordance that have all biological adaptations are affordances that have been seized and grafted into living things, typically by heritable variation and natural selection. So right now we're talking about a zombie universe in which no organism has a mind. Adding minds is another issue. Okay, so where we got to was to say, we don't think you can use set theory with affordances. So let me tell you about the uses of screwdrivers. I may have told you this, Perry, but here it is. I'm going to hand you right there in Chicago a screwdriver. It took me a long time to find this discussion, and I've been writing about it for about 8 years now. Tell me what you could do with the screwdriver right there in Chicago.
Well, I can, um, if it's a flathead screwdriver, I can do flatheads, but I might be able to do a Phillips if I twist it a funny direction, right? I could pry open something that's glued shut. I could conk my dog on the head.
Yeah.
I could use it as a chisel.
Yeah.
Right. I could get some paint off of a piece of wood.
Yeah.
It wouldn't be very good at it, but it would work. Or I could hold the skinny end and use the fat end as a hammer and drive a nail.
You're doing really good. So I've now thought about it for a long time. So let me go on. All right. You can use a screwdriver alone or with other things. So for example, you can short out an electric circuit with it, right?
Yep.
You can scrape putty. You can wedge the door open. You can wedge the door closed. You can break the window. You can tie it to a stick and spear a fish. You can rent the spear out to the locals and take 5% of the catch. And my favorite is you could lean it against the wall, angled out. You can put a piece of plywood leaned up against it and put a wet painting underneath it to keep the rain off of it. That's a dandy use of a screwdriver. So do you think the number of uses of a screwdriver is some specific number like 14? Is it infinite? Or do you think it's indefinite?
Well, I know a little bit about, like, mathematicians have this whole,
Go there.
they have entire books about infinity, so I'm not going to go there.
Yeah.
I would say it's indefinite.
The interesting thing is that we all say it's indefinite. Let's hold that. And then we'll get to why it's indefinite. And one of the reasons to get to first order infinity, you need the notion of n and n plus 1 in induction. Okay, so let's take indefinite. The next thing to point out is there are four numbering scales. A nominal scale, it's just the name of things. An x is greater than y and y is greater than z. So x is greater than z is a transitive relationship. An interval scale like a thermometer, but you don't know what 0 is, and a ratio scale where twice this is that. So what kind of a scale is the uses of screwdrivers? It's just a nominal scale, right?
Yeah, okay.
There's really crux. There's no ordering relationship, it's just a bunch of different uses.
Oh, hang on. So you're saying that there's nothing to tell me that shorting an electrical circuit comes before chisel in my list.
Yes, you got there, right. So I made the claim some years ago that therefore no rule following procedure, no algorithm can list all the uses of a screwdriver alone or with other things in Chicago today, nor can it deduce one use from the other use. You cannot deduce from the use of a screwdriver to screw in a screw, the use of a screwdriver to tie to a stick and spear a fish. There's no deductive relationship between them, okay? So now I'm going to go on to the world is not a theorem. Then later, if you want to, we can try to get to how that leads us into the fact that there's no final theory. So about 2 months ago, I started thinking, can you use set theory with affordances? So Andrea Roli is this now quite good friend of mine in Italy. And we decided to ask, can you use set theory with affordances? So here's an axiom of set theory. It's one of the fundamental axioms. Two sets are identical if and only if they have the same members.
Okay.
Okay, so now let's consider the use of a screwdriver and the uses of an engine block. So I'll tell you some uses of an engine block. You can drill holes in it and make an engine. It's rigid, you could use it as a chassis to make a tractor. It's heavy, so you can use it as a paperweight. And as you know, it's got sharp corners. You can use it to crack open coconuts, which I'm very fond of. So now let's ask the following question. Let's consider the indefinite uses of an engine block and the indefinite uses of a screwdriver. Can we prove that the uses of the engine block are identical to the uses of the screwdriver? No.
That would be impossible.
It's impossible, right?
Right. It would be not possible.
It's not possible. It's not possible. Therefore, we cannot use the axiom of identity. We need the axiom of identity to do set theory. So take that in.
Okay, so could you give me a second? I would like to try to give people a sense of where we're going with this, because this is actually very profound.
Yep.
Give me a sec. So
and really weird.
It's really weird, but it's also not that hard to understand. Okay.
No.
So
what you say, oh yeah, now what?
Right. So here's kind of where this is going. There's been an assumption going all the way back to the ancient Greeks that if we just analyzed everything enough, we would know everything. Right? If we can measure everything with enough precision, and if we could see how fast all the particles were moving, and if we know where they came from, that we could figure out where they're all going, and the world would be completely predictable. And wouldn't that be like the best use of science to make the world completely understood, completely predictable, and get everything done in numbers and math? And there's a lot of people who think, yep, that is exactly right. That's what this is all about. And it might take us a long time, but we're going to get there. And it's all numbers and math, and it's all analysis. And there's lots of scientists believe that, lots of physicists believe that. Where you're going with this is you're using these really weird things about coconuts and engine blocks and screwdrivers. So set theory in mathematics, there's something called Frankel-Zeno set theory or something like that. And it can basically, you can start with that and you can build almost all of mathematics just with like these very basic ideas of these numbers are in this bucket and these other numbers are in the other bucket. And it's like the rudiments of math. And so you can build math with it, and then you can build physics with it. And what you're saying is, if we're talking about opportunities and we're not talking about rocks, if we're not just counting atoms, if you define something as an opportunity, which you're calling an affordance,
seized by an organism and they really come to exist in evolution. Hearts
right.
Actually came to exist.
An affordance cannot be reduced to sets, which means it can't be reduced to mathematics, which means anything in the realm of life defies reduction to mathematical analysis.
Yes.
Is that right?
Anything having to do with the becoming of evolving life. Once life exists, like your heart, I think you could probably explain how a heart works with physics. Sure, yes, you can explain how a heart works with physics and chemistry and stuff. The becoming of life is not going to be, it's just wild. So let's look at some more set theory. So we can't do the axiom of identity. Another axiom is there is a zero. Oh, we're going to try to get to whether we can do numbers. So there's two ways to do numbers. You could define the number one as a set of all sets having a single member. Okay, that's Russell. You just got a bunch of sets, and every set has one apple, another set has one banana, another set has one screw. Well, okay, so we want to form the set of all objects that have a single use. Here's a screwdriver, and it really has only a single use. And here's a rocket, it only has a single use. You can't do it because the number of uses is indefinite, right? So you can't do the number one. Well, you can't do
So
the
you're
number.
saying, again, Stu, you're saying pick any, okay, I got a marker, I got a wallet, I've got a cup. There is
Tell me,
nothing in this room could be said to only have one use.
yeah, you could, right. And therefore, by the way, you can't get the null set for set theory and for arithmetic. Peano's axioms. Andrea and I are looking at Peano's axioms because everybody should look at Peano's axioms, before dinner. You need a zero element. So a zero element is a set that has no members. So what we need to do is form the set of objects that have no uses. So we can't do that. Then you need something called a successor relationship, as in n and n plus 1. So if you do an n and n plus 1, then you can start with 0 and get to 1, then you can get to 2, then you can get to 3. But we agreed that the uses of a screwdriver, it's also true for an engine block, it's a big step to get there, are not ordered. But then there's no successor relationship. There's no successor. So we don't have a zero element and we don't have successor. So we cannot do numbers. So we can't do the integers. This just gets so wild, Harry. We cannot do the integers. So we can't do ratios and we can't do equations. So we can't get to irrational numbers by the Pythagorean theorem. You know that the triangle with the two sides are 1 and the second and the sum of the squares of the first two sides are equal to the square the hypotenuse. You need to take the square root of the hypotenuse and it's an irrational number. Well, we can't do that. So we can't get to irrational numbers. Well, we're going to need irrational numbers to do quantum mechanics. We can't get to sets. We can't do combinatorics. We can't do the union of the set of uses of an engine block and the union and a screwdriver. We can't do the intersection. So we can't do first order logic. So we can't get manifolds and smooth surfaces. So we can't have equations. 2 plus 3 is equal to 5, or 2 plus x is equal to 7. What's x? So we can't do differential equations. And we can't do the theorem of choice, which is nutty enough. Here's the theorem of choice, the axiom of choice. And you need it for a bunch of things. So it takes a while to get the axiom of choice. When I first read it, I thought only mathematicians would think of the axiom of choice. Here's the axiom of choice. You have some large number of sets. Each set has some integers in it. So one set has the integers 2, 7, 9, 83. Another set has the numbers 13, 18, 42, whatever. Well, the axiom of choice says there's a procedure, an unknown procedure, that allows you to pick a unique member from each set and use that to form a new set.
Okay.
So I understood that because here it is. Take the smallest integer in each set and form a new set. Okay? Well, you can do it with integers. You cannot do it with affordances. And the reason is there's something called the well-ordering theorem. The well-ordering theorem says, suppose that you've got a bunch of integers in some list. There's a way of rearranging them so that any number can become the least number. And you need well-ordering to get to the axiom of choice. But there's no relationship among the different uses of things, so there's no way to order them. So well-ordering fails, so you can't do the axiom of choice. You can't do mathematics in any way that we know it. You can't do category theory. I think you can't do topos, whatever they are. You can't do it. So this is meaning something amazing. The biosphere is, well, we have to get to the fact that cells construct themselves. So we'll get there in a minute. Anyway, the biosphere is constructing itself, which I'll explain in a moment. And it constructs itself and has become incredibly complex in the last 3.7 billion years. And as far as I could tell, we could do no mathematics whatsoever with respect to what specific will get constructed. It's just wild.
So can I jazz improvise with you on this?
Jazz improvise. Okay. We need construction, Barry. We
So,
need constraint measure.
so here's dotted line. You got this column, this column. So over here,
I
we
got the dotted line. That's pretty cool.
math,
Yeah,
physics,
yeah,
chemistry,
yeah,
all of that stuff. Okay.
yeah.
Over here, we have biology.
Evolving. Well, by evolving life, it's diachronic. It's across time. It's not what life is at any instant.
Okay. Okay. All right. Great. Okay. Evolving life.
Mhm.
Let's see. Okay. So all of this stuff. Okay. I'm also going to put computation.
Yep. Computation, and we're missing construction on the left side. The big difference is that living systems construct themselves, and construction is not deduction. I'm very proud of thinking up that pair of words.
Yes. Okay.
And
now,
if that construction is greater than deduction, I'm also proud of that. You use one of these little carrots that means greater than.
no, Stu, you don't know this, but I've been thinking about this in my own way for 15 years already.
No kidding.
Not the way you put it, but let me just take a little bit of a little tweak here.
Yeah.
Okay. You and I, we're talking on Zoom, and about 80 years ago, guys like Claude Shannon and Nyquist figured out that any sound could be chopped into little pieces and reduced to numbers, which is why everybody can hear us talking. And any picture could be chopped up and reduced to pixels, which is why I can see you. Okay?
Right.
And so, like, I don't think 100 years ago, nobody really imagined that a computer, if we just had a little calculation machine in our pocket, that we could talk to people on the phone and watch YouTube videos and all that kind of stuff. Okay. And so what that means is that any signal can be reduced to numbers, but the meaning
It's gone. Yes, it's all syntactic.
Yeah.
Information theory, all of mathematics, and this is Hilbert's formal program, that all of mathematics is get rid of all the syntax, all the semantics, and let's just do syntax. It's worth going into why mathematics got there. It's in the talk that I just gave at the Karolinska. Let's take a few minutes and just say it for everybody. So it's 5,000 years ago, and the Egyptians are out after the Nile floods making triangles in the mud, and the angles add up to 180 degrees, kind of. Well, around 300 BC, Euclid, who was an Alexandrian Greek, I learned, did the elements. It's the first amazing deductive theory, and it's exquisite. Furthermore, it's true of the world. It's really true that triangles add up to 180 degrees and so on. And it's true of the world. So for 2,000 years, mathematics is the queen of the sciences, because by sheer thinking, you actually know about the world. Until around 1850 or so, when Gauss didn't publish it, and I guess it's Lobachevsky, two mathematicians doubt the parallel postulate, the fifth axiom, rather, that says given a straight line and a dot off of it, you can only draw one line that's parallel. And so one of them says, no, you can make a curved line that goes through 2 points. And the other says you can make a curved line that doesn't go through anywhere. And they try to deduce a contradiction, and they can't. And it just tears mathematics apart, because mathematicians realize, my God, you can have a mathematical theory and it has nothing to do with the world. Nothing. Now what? So then there's all this effort to say, well, when do you know it's about the world and when not? And you want to have a model of it. And then Hilbert comes along and says, forget being about the world. That's a semantic part. Just don't bother. Let's talk about a system of a set of symbols and a set of axioms and a set of rules to manipulate the symbols given the axioms, called inference rules. And the question becomes, forget the world. What we want is a set of axioms and inference rules, and we want it to be consistent and complete. Well, what does consistent mean? It means you can't deduce a contradiction, which is a good idea. If you deduce a contradiction, you can deduce anything mathematically. They want it to be complete, which means every statement that is true, given the axioms, can be derived as a theorem from the axioms. If that's true, you're set. So about 10 years later, Gödel comes along and says, well, no. So he constructs the Gödel's theorem, and he manages to get a sentence to talk about itself by using something called Gödel numbers that I don't understand. And the sentence says, listen, if I'm true given your axioms, you can't prove me as a theorem. And apparently Hilbert found out about it. He said, we're going to spend the rest of the time finding out why I was wrong. But Gödel does something even worse. He says, look, the system has to be as rich as arithmetic, apparently, the axioms. He also says, so here's a statement that says about itself, if I am true, you can't prove me. So you can't prove consistency. And he says, if you take the new statement and add it as a new axiom, you get a new system, which again generates a statement that says about itself, oh yeah, well, if I'm true, I'm not provable from your new axioms. Odd forever. So in fact, Stephen Hawking got worried about it. He says, how do we know we'll ever get the true theory? Because maybe Gödel's right. So where else I've gotten to in the PowerPoint that I've sent you is the evolving universe with an evolving biosphere instantiates Gödel's theorem.
Yes.
There is no final theory. I'm pretty confident I proved it. Not enough yet to have, not to have the drink, but at least a hot dog. So I'm asking people to, it's so strange, Perry. So let me just say the rest, because it's really kind of easy. Well, it's not easy. So it has to do with work and work cycles and constructing things. There's no construction in mathematics. I'm sorry, you wanted to say.
Well, okay. I just want to make it clear. So, and I think I've read Stu's paper, and I think he's right, because I've come to the same conclusion, a different route myself. And what we've got is that we've got this dotted line here, and it says that nothing on the left side of the dotted line can be reduced to math.
Nothing on the left side, which is an evolving, self-constructing, co-constructing biosphere,
right,
can be reduced to mere deduction. It's not syntactic, it's construction.
Right. Now,
wild.
If you have defined science as getting everything in the world into this shoebox, which a lot of scientists,
everybody does since Newton.
Okay, if you think that that's what science is, then Stu just nuked your entire worldview and leaves you wondering, well, what now? And like this happened in mathematics when Gödel introduced his incompleteness theorem. A lot of people just wanted to wish that it would go away.
It's worse than that. It's true. It's worse than it's not a formalism, but it seems to. So there's a plan. Andrea and I, you can get in on this, Barry. We are buying a very small island on the northwest coast of Newfoundland to hide. I told you about this. But it turns out it's actually a good economic investment, because I'm an old Jewish guy, and the Arctic Ocean is melting, and tankers are going to come through, and we can sell latte to the ships coming. It's going to be worth a fortune.
And nobody will be able to kill you because you'll be too far away from civilization.
That's the whole point. But look, let's get to the rest of it about construction. So, so the way to get into this is what is thermodynamic? What is work? Well, Atkins says, physicists say it's force acting through a distance, and Atkins in the second law says it's more interesting than that. It's the release of energy into a few degrees of freedom. A degree of freedom is a possibility. So I can understand that. Think of a cannon and a cannonball and the powder behind the cannonball, and the powder explodes, and it doesn't go out as a spherical explosion. The only way left, the only degrees of freedom left is blasting the cannonball out the bore of the cannon. So work is done on the cannonball.
Mm-hmm.
And what the physicists do is they say, of course it is. And the cannon is a boundary condition, a fixed boundary condition, and the ball is a moving boundary condition. And they put in the boundary conditions and they solve for the work done. So about 20 years ago, I asked a funny question. I said, where'd the cannon come from? And then you think, with the Big Bang, there were no cannons. So here's what I read, it took work to make the cannon. Somebody made it.
Yeah.
So I get to a cycle. No constraints for sure, no work. No work, maybe always no constraints, or no work, often no constraints. So you use work to construct constraints. Got it? So that's a work constraint cycle. It may be the case that it always takes work to construct constraints. A low energy structure like a solid can be a constraint. I don't know if it took work to make it. Maybe you had to have a gas source. In any case, what I want to say is it's surely true that no constraints, no work. And it's surely true that often it takes work to construct constraints like the cannon.
Mm-hmm.
Then I got as far as saying, okay, and when work is done, it can construct a new constraint. I mean, the cannonball can go out and bend a piece of metal that becomes a hook that you can use for something. Yep. And I got stuck there. I should have known the answer, but I didn't get it. And Matteo Mosio found the answer in 2015, 15 years after I didn't figure it out. So here's the idea. It's one of these stunning ideas, and I love them for it. I'm not even peeved that I didn't figure it out, which is too neat. So imagine so work is the constrained release of energy. So you have to have some non-equilibrium processes to constrain them. So let's have n non-equilibrium processes and n constraints. We're going to use each constraint on the release of energy of one of the non-equilibrium processes such that the non-equilibrium processes construct the very same n constraints. The set of constraints constrain the release of energy that constructs the same constraints. It takes a while to wrap your mind around it. It's so simple and beautiful. So let's take three. So there's non-equilibrium process 1, 2, and 3, and three constraints, A, B, and C. So A constrains process 1, and it makes a B. Well, B constrains process 2, and it makes a C. And C constrains process 3, and it makes an A. Do you feel it? What's happening is...
It would help if you gave it like an example, like...
I'll give you one. Okay, so years ago, I came up with an idea about the origin of life as a set of molecules that mutually catalyze one another's formation. So if it's you and me, Perry, I catalyze the formation of you out of 2 Perry parts, and you catalyze the formation of me out of 2 Stu parts. Okay. And it'll work if we feed in Perry parts and Stu parts. So that is a collectively autocatalytic set. You catalyze the formation of me, and I catalyze the formation of you, okay?
Okay.
Well, they actually exist. People have made them out of DNA and RNA. Gonan Ashkenazi, who was at the StuFit, no, he wasn't. Gonan Ashkenazi yes, he was. Gonan has made a 9-peptide collectively autocatalytic set. So peptide 1 catalyzes the formation of a second copy of peptide 2 by binding the 2 fragments of peptide 2 and ligating them together to a second copy of peptide 2. Then 2 catalyzes the formation of a second copy of peptide 3 by binding 2 fragments of peptide 3 and ligating them into peptide 3, and so on around, and 9 does it for 1. It's a collectively autocatalytic set, okay? Thermodynamic work is done because the peptide bonds are formed, and the constraints are the peptides themselves. And Matteo and Mile pointed it out. An enzyme is a boundary condition, which I didn't realize. It binds the 2 substrates So they don't float around in three space, they're bound to the thing. And then having held them near one another, that lowers the activation barrier for the reaction to happen. And the reaction proceeds in a given direction with the release of energy. So an autocatalytic set, say of peptides, automatically achieves catalytic closure. Every reaction that has to get catalyzed does. It automatically achieves constraint closure, which is why I should have realized it in 2000, because I was working with autocatalytic sets, which we're trying to make. So a self-reproducing set of molecules, for example, Joanna Xavier, you're talking to Joanna. Joanna has found a set, an autocatalytic set of about 1,500 small molecules in archaea and bacteria, and they mutually catalyze one another's formation, including some iron sulfate and stuff. So I'm pretty sure life starts in the universe that way about 5 billion years ago. The Joanna set, if I can call it that, without any polymers in it, is collectively autocatalytic. When the molecules are acting as catalysts, the whole thing is achieving constraint closure. Once you have molecular reproduction, you have construction. The system constructs itself. It's not describing itself. It's doing thermodynamic work to construct itself. Automobiles are constructed by us. Our cells construct themselves. And the biosphere is a system of self-constructing things called cells and organisms that make niches with one another. And the biosphere constructs itself. This was in my last book, A World Beyond Physics. It's really strange, Perry. People are having a hard time grasping it. We are so used to equations. I'm sending this to very good physicist friends. I think they're getting it. It's hard. So there's a few more pieces of it now. With a Kantian whole, the whole exists in the universe formed by means of the parts, said Kant.
Okay, so let me just, can I put work?
Yeah, well, work and so there is work and there's constraint closure, a system that constructs itself. Living systems construct themselves.
So I'm going to put self-construction.
Yeah, the big step is that living things literally construct themselves.
Right. If you could put a fork in your mouth, you are constructing yourself. Because
I don't know.
You went and got food.
Oh,
right?
yeah.
And you're
yes.
Right.
You said a growing embryo is constructing itself, right? You have a fertilized egg. It doesn't describe itself. It doesn't compute itself. It constructs itself.
Yes. And that is not analysis.
No, it's not analysis.
Right. So that's very important. Now, that's a good time to bring in Kant. So explain what Kant said 200 years ago and what does it have to do with this?
Well, so Kant's so amazing. I just have to tell you a story. I was a sophomore at Dartmouth, and I was listening to Fran Gramlich give a lecture about Kant with I won't tell you my friend's name. He was my age, but a year younger. And so my friend is a freshman. We walk out of the hall. I'm thinking Kant's the most brilliant mind since Aristotle. And my friend says, Kant's for shits. And I thought it was great. My friend, sort of disposed of Kant. It's just so cute. Anyway, among many things, Kant says there'll never be a Newton of biology. And here's his words. I'll remember which one it is. Anyway, it's an organized being then has the property that the parts exist for and by means of the whole. They exist in the universe for and by means of. He didn't say universe. I'm adding that. It matters in the universe, Perry, because we have human hearts. The universe is not ergodic above the level of around 500 Daltons.
But you'll have to explain that.
The universe will never make all complex molecules. It's made molecules up to about, small. It's made all small molecules. It's not made all possible large molecules. It never will. in vastly longer than the history of the universe. I'm just finishing a paper with Lee Smolin and Marina Cortez and Andrew Little, where we're going to say this more firm, but I've been saying it a long time. Then why are there hearts? Hearts are really complicated. And the answer is life started, living things are Kantian wholes. You're a Kantian whole. You exist for and by means of your heart and your liver and your kidney and your spleen, but they exist because they're part of you.
Mhm.
So you're an autocatalytic set and you achieve constraint closure. When you evolve, you bring along with you the parts that sustain you. That's why there are hearts. Life started, hearts evolved because they sustain the organisms that have them, and your kids will have your organs, more or less. That's why there are hearts in the universe. It's because we're Kantian wholes. Statement one. Statement two, they construct themselves. Mile and Matteo are right. So it's construction, not deduction. The next thing is you could define the word function. The function of your heart is to pump blood, not wiggle your pericardial sacs water or make heart sounds. The function of a part is a subset of its causal consequences. Okay? This is really critical. And we're going to need it. So the function of a peptide in Gonin said is to catalyze the next reaction, not jiggle the water in the Petri plate. Okay, so now we've got that step. So now we've got cells evolving, and I have to tell you about Darwinian preadaptations. So Darwin said adaptation. Then he said, you know, an organ might have a function, but it would have other causal features of no selective significance in this environment, which might turn out to be useful in some other environment. So an example is hearts are resonant chambers, and maybe your heart can pick up earthquake pre-tremors and you're in LA, and you go outside and survive and everybody else dies. So then you marry a lot of girls because you're famous, and pretty soon there are earthquake detectors in human hearts. So that's a silly example of a Darwinian preadaptation. Well, they're happening all the time. Evolution is full of Darwinian preadaptations. Perry, they're jury rigging. Jury rigging is putting together a bunch of things so that they accomplish something by weird uses of their causal features to accomplish some test. Evolution is full of jury rigging. But now, so let's jury rig, and this takes us back to the screwdriver. You cannot deduce the different uses of screwdrivers and their causal properties to accomplish something. So we're back to the engine block. There's no deductive relationship between the use of an engine block as a paperweight and its use to crack open coconuts. Make them molecules. Evolution occurs not with abstract symbols, but with actual physical things like molecules. Any molecule, any object, any real object has more than one causal property that cannot be deduced from one another. But that's what happens in evolution. Evolution goes from using an engine block as a paperweight to finding a way to use it to crack open coconuts. There's no deductive relationship. Therefore, evolution is not a deductive procedure. Therefore, no laws entail the evolution of the biosphere at all.
Evolution is not computation.
It's right, it's construction. And it's so weird to realize it. We've spent all this time forgetting construction, and we do it all the time. So,
which is why you say construction,
not deduction,
not computation.
Not well, construction can't be deduct. And anyway, so what this implies is the following: the biosphere is evolving, and it's finding ever new uses of things like new proteins. The biosphere is making new proteins. New proteins are new boundary conditions, which are constructing new phase spaces, or what is next possible. So in physics, everything is done in a pre-stated phase space. Lee Smolin taught me this. Everything does in physics, because you've already said what the space of possibilities are, and now you get some sort of trajectory in it. In classical mechanics, it's a deterministic trajectory. In quantum mechanics, it's a deterministic propagation of a probability distribution and the weirdness of measurement. So Giuseppe Longomile Monteville and I realized and published in 2012, the biosphere is constructing ever new and not prestatable phase spaces. And Perry, I've been saying unprestatable for years. I finally understand it. The reason it's unprestatable is that you can't do set theory.
Well, hang on. What do you mean prestatable? What does that mean?
You can say ahead of time what you're talking about. So in quantum mechanics, you could say ahead of time for any quantum system all the possible amplitudes given the Schrodinger equation.
Oh, okay.
But what's so strange about the evolution of the biosphere is you cannot say ahead of time what will come to exist.
Okay, so if I got a pool table, I could pre-state all the things that the pool balls might do. All I have to do is figure out all the directions my pool stick might point.
Yeah, even more simply, the boundary conditions of where the table is define the phase space of all possible positions of momenta, right?
Right.
Given the boundary conditions, the phase space, well, cells construct their own boundary conditions, so they're constructing their own ever-changing phase spaces. And that means that new in the universe possibilities arise because cells construct them. They weren't there beforehand. They weren't there in a Hilbert space before the universe formed.
Okay,
They're new in the universe possibilities.
This, back to jazz improvisation.
Yeah.
This suggests that there is some part of this that is non-computational, that has an origin somewhere else besides computation. Like there's a lowest common denominator. Now, in my work, I say that it's choice because only choice can assign meaning. But I've never talked to you about this, and I don't believe you talk about it in your paper. So we're kind of off of a reservation here. But
well, we're not.
Oh,
so
okay.
let's get it into the zombie biosphere. Okay, so there's no mind yet. We want to get to mind, but we don't have mind yet. So we have quantum mechanics, and so we have a quantum mutation in some DNA molecule.
Okay.
Which changes a protein. So specifically, flies have red eyes, and there's a mutation in the DNA that makes the eye white. It's an actual mutation called white. So it's recessive, but call it dominant. So now we've got a white-eyed fly, all right?
Okay.
Suppose the white-eyed fly is fitter in its world than the red-eyed fly. It's good near a winery. So 1,000 years later, you've got an incredibly large number of copies of this funny DNA molecule in the universe. Okay?
Okay, right.
The evolutionary process by which the white-eyed fly won out over the red-eyed fly, they're all zombies, is a choice that is being made by the evolving biosphere.
I'm not sure I'm ready to accept that the fly is actually a zombie, because
no, I'm not either. I'm saying suppose in the worst case it's a zombie. I actually think it's perfectly conscious. The point I'm making is that in evolution, an opportunity can be seized by heritable variation and natural selection. And that's happening all the time in evolution with a bunch of zombie organisms. Well, we aren't zombies. We aren't zombies, and we actually make choices, which is where you want to get.
I am not convinced that in a zombie world that actually works.
Well, no. I'm not either. And that's why I'm trying to go there with Andrea Roli. What we're trying to show is we're about to publish a paper saying, well, it follows from what I just said. So this is Andrea and I are about to write this. So it's Andrea Roli. We're about to say because of this that strong AI will never happen. And the reason is strong AI is always deductive. Mm-hmm. But if you deduce from suppose the computer knows that you could use an engine block as a nifty paperweight. Well, the way Andrea says this is a program has objects. Objects can spawn new objects. Objects have properties, but there's no way to get new properties. So I'm speaking for Andrea. Therefore, the computer can do something like figure out all the combinations of everything you can do with all the properties. But if it doesn't have the property in it, its ontology under it, it'll never get another one. So if it doesn't already have that you can use an engine block to crack open coconuts, it can never get it, which means no formal system can do it, which means we're about to publish strong AI will never happen. That is to say, we are able to do something that isn't a logical inference. It's not a deduction.
I completely agree. Totally.
By the way, I think I know what it is. I think it's that mind body is associated with a mind brain state that is quantum entangled with the world.
Mm-hmm.
Quantum collapse happens. Mm-hmm. Collapse is not a deductive process. Mm. And my increasingly firm bet is the collapsed state is experienced as a qualia, and it's a single state. And David Chalmers points out that qualia are never in superposition. And he wants to say there's something about conscious awareness that has to do with collapsing the wave function. I do too. So where I want to go with this, Perry, is I want to show, I think we can show, that no classical, we can certainly, well, we believe we could show no universal computer that is not embodied can see affordances that are new affordances. Like, you can laugh at the fact that you could use the engine block also to crack open pineapples and pine cones. Well, a computer can't do that. So if we can show that no classical dynamical system can see affordances as we can, then we are not classical dynamical systems. Therefore, mind better be partially quantum. And meanwhile, Dean Radin has all sorts of evidence that mind is partially quantum. We have a paper online, Radin and Kauffman, saying, is mind-brain quantum a theory and supporting evidence? It's on arXiv. It may or may not get published. People have done work on quantum features of mind for a long time. Non-locality, spatial and maybe temporal non-locality, says, of course, if we can be entangled with one another, of course telepathy is possible. I've actually experienced either that or precognition. There's an amazing amount of data for it. I want to come in on mind in two different directions. One is the stuff that Radin and others have done, saying mind is quantum. I think I've answered the problems from Descartes' dualism. If you think of res potentia and res extensa, which is what Heisenberg said, the quantum state is about ontologically real possibles, which I came to also, along with Ruth Kastner and Mike Epperson. If you take the view that ontology, the world consists of ontologically real possibles and ontologically real actuals, and measurement converts a possible to an actual. I more and more think that's right. It explains 6 or 7 of the mysteries in quantum mechanics, like non-locality and so on. If you take that, then there's a natural hypothesis about what mind does. It converts possibles to actuals. And that is the choice. The choice is, so the other astonishing thing that Dean's done is he and others have done the following experiment. You're sitting next to him in the 2-slit experiment, and he says, Perry, look, try to alter the intensities of the central light and dark bands. And you try. How do you try? I don't know. The answer is, it's been done about 28 times. The overall statistics at this point are 1 in 50 million. Well, you got to worry about meta-analysis and other things. But 1 in 50 million is getting good enough to think, maybe. Well, if you can try and collapse the wave function, you're altering the world. Mm-hmm. Now you can maybe have a responsible free will. So, I hope we get enough data so that we're absolutely convinced. Meanwhile, the evidence for telepathy and the evidence for precognition is out at around 7 or 8, maybe 6 or 7 sigma. The stuff on this stuff with the 2-slit experiments at 5.2 sigma. 5 sigma is a success at CERN. There's stuff on random quantum number generators. And when Nelson Mandela dies, random quantum number generators go wacky, where the evidence is out at about 7.3 sigma. There's another interpretation of it that I don't quite understand. The Dean says take some kind of funny non-local something. So the experimental evidence for quantum features of mind are getting strong. I'm hoping I can push with Andrea the argument that classical computers cannot see affordances. We can.
Mhm.
Well, surely we'll get it for unembodied universal Turing machines. The step is to show that no classical dynamical system can see affordances, and we can. So we're not just classical.
Mhm.
If you can come in on a pincer movement that says, okay, we can see affordances and classical systems can't, so it must be quantum what's left. And meanwhile, there's evidence for quantum, so neat. And I'm coming to like more and more the idea that we see affordances because our mind brain is entangled with the world. It's a huge superposition and it collapses and it's experienced as a qualia. I don't know that it's right, Perry, but it hangs together. So it's attractive, maybe
Well,
more.
Stu, okay, most of what you've said here, I completely agree with, and I have come to almost identical conclusions using very different, origin point. And this is revolutionary. We are talking about literally redefining science based on what a lot of people define science to be.
Right.
If it turns out that nothing in the evolutionary world can be reduced to computation, including evolutionary biology, and
Right.
that therefore means all of the soft sciences
Are legitimate.
are legitimate,
Isn't that wild?
and that the certainty, and for decades there's been this phrase physics envy, which is biologists wishing that biology was as precise and neat and clean as physics, is like, get over the physics envy, because it's like, well, it's almost like, yeah, I don't know a good analogy.
Well, look, but meanwhile, look, I've been struggling with this for a long time. So physics works perfectly well.
Mhm.
It's general relativity is confirmed to 13 decimal places, and so is quantum mechanics. Quantum field theory works. Particle physics works. Everything is confirmed.
Mhm.
It's fine. The big step is constraint closure, that living systems construct themselves, and that is irreversible. The underlying laws are reversible. You could find the bones of dinosaurs 60 million years later. It doesn't look too reversible because of construction, right? And
Yeah,
construction is nowhere in physics.
that's right.
And mind you, that's all with zombies. Okay, that's true for a zombie evolving biosphere, which lifts itself above the abiotic universe because things construct themselves. Then we got to get mind into it. Mind's been gone since Newton.
Well, Newton wouldn't have been too happy about that, but he didn't get to choose how history decided to interpret his work.
His
He was,
work, he's got to be the greatest scientist who's ever lived.
so
Einstein.
yes. So this is extraordinary. I think I want to end here. But
Yeah.
but actually, let's just put one more. You said at the very beginning, you said, I don't know if I'll ever get this published, but I'm going to try. Could you speak just for a minute about the politics of getting something like this through the big system out there?
It's going to be hard, Perry. So publication is just fine. It's peer reviewed. Actually, Andrea, with respect to the world is not a theorem, Andrea Roli and I submitted it to a journal. I won't tell you which one. And we got back an absolutely wonderful review. It's a 6-page review that entirely missed the point, completely. Everything the person said was really perfectly smart. He said, look, you can do mathematical models of biology. I mean, there's mathematics about cardiac behavior and this and that and the other thing. He's right. He doesn't have the idea of construction. Well, we didn't have that in that paper. It takes a long time to see the world in a new way. This I'm going to say something funny. It turns out that when Newton invented classical physics, he was lecturing at Cambridge. Perry, nobody came to his lectures. They hadn't apparently, they had the faintest idea what he was talking about. Like, what's this guy? What are you talking about? We want to talk about Aristotle and music. What's he talking about?
Wow.
This is, this, you know, I don't even know what to say. I do know what I think. I think that if this is right, and I do think it's right, but now what has to happen is a bunch of people look at it and say, yeah, it really is. So, as always one says, let's wait for really severe criticism. If it's right, it's an enormous step of a scale somehow that is like classical mechanics and quantum mechanics to something else that has a radical freedom to it. Living systems construct themselves, entailed by no law, into an unprestatable adjacent possible. I've been saying it for years and I understand it better. We have the Greek notion of human rationality, which is, of course, the peak of the Enlightenment, right?
Mhm.
Well, I've understood for years, but now I really think I understand it. Not only do we not flip a coin 100 times, you don't know if it'll come up 53 heads or not, but you can calculate it.
Yeah.
As Giuseppe Longo taught me, you know the sample space of the distribution, so you can define random. And Giuseppe taught me, with respect to what you're talking about here, you can't define the sample space, so you can't define random.
Mm-hmm.
Not only do we not know, and I've been saying it for years and now I understand it, not only do we not know what will happen, we don't even know what can happen.
Right.
And what is
Right.
what is reason if we don't even know what can happen? And all you got to do is talk to a venture capitalist like my cousin Rich, who talked at the Stew Fest.
Mm-hmm.
They can't calculate what's going to happen when they put their money down
No,
because they don't know what the possibles will become.
no,
They
no.
can't. So humanity is more than deduction, and it's more than induction, and it's more than abduction. Abduction, you have to have the thing and how the parts work together. It's something wildly different and more. My friend Mike Gottschalk, who he's my theological thinking friend who also repairs houses. Mike's just magical. He said, look, there's two principles: causality and creativity.
Yes.
And the present is the frontier between causality and creativity. Isn't that lovely?
It is.
And he's exactly right. Lee Smolin is getting to something kind of like that. Marina Cortez and we're all getting to something that is so strange. It's this open creativity of a universe or a biosphere that's becoming with no final theory. And instead of it's being, in fact, Andrea and I are realizing it's not a loss, it's this wondrous gain.
Yes. As soon as you have to live with the certainty.
Yeah. Yeah.
Yes,
Kate,
that's beautiful.
Kate and I taught, I taught at the Harvard Divinity School. Catherine was a student there. My colleague was Gordon Kaufman, a relative, who wrote this wonderful book called In Face of Mystery. Mm. Isn't that lovely? I'm sort of almost speechless having babbled. It's so strange, Perry. I don't know what it means, but one begins to understand something that's wonderful. And somehow with it, maybe here we are in the Anthropocene, destroying the planet, okay, using resources beyond what the planet can afford. Maybe something like this is part of our seeing ourselves in the world in a new way. We really are co-creators of the biosphere with everybody else.
Mm-hmm.
We're not masters.
Yep. Well, Stu, this has been fantastic. Thank you for turning 300 years of physics completely upside down. We only did it in an hour.
Pretty good. So now what are you going to do with the podcast?